Our next speaker is from Phoenix, Arizona, who graduated from Arizona State University and is currently a first-year perfusion student at Midwestern University. He is heavily interested in trauma and would like to work at a level 1 trauma center in Miami or even New York City after graduation. He is currently wrapping up his first year and will be starting clinical rotations in June, where he will learn more about the field of perfusion. Please join with me in welcoming Cesar Delgado, speaking on validating effectiveness of the biocompatible circuit coatings by measuring biomarkers of platelet activation during cardiopulmonary bypass.
Awesome. Thank you very much for that kind introduction, Susan. I just want to thank everyone on my team, starting out Dr. Darbin, Caitlin, Miguel, and Amy for all their help throughout the experiment. And they're definitely play a huge role in making everything possible in terms of data analysis and running the experiments and coming up with ideas to make every experiment better. And so this is actually a pilot study that I'm excited to talk to you guys about. It's called Assessing Biocompatible Circuit Coatings Using Biomarkers for Platelet Activation During Cardiopulmonary Bypass. Perfect, but before we dive right in, I just want to give a little bit of a background exactly what we're getting into here. So as perfusionists know, one of our biggest concerns during cardiopulmonary bypass is activating the SIRS, which is the systemic inflammatory response syndrome, which can be detrimental for our patients. It can cause a variety of organ dysfunctions, and failure to attenuate this inflammatory response intraoperatively can result in renal injury, GI injury, myocardial dysfunction, coagulopathy, hemolysis, embolism, edema. As you can see, there's a lot of comorbidities that can be caused by the systemic inflammatory response during cardiopulmonary bypass. And if you look on the right, you can kind of see a little bit of indicators that would suggest SIRS. Some of them don't pertain to us specifically as perfusionists, such as the respiratory rate, since we're the ones that control the patient's respiration during cardiopulmonary bypass. However, there's some stuff that you would see in the ICU afterwards, and it can be very detrimental to our patient. In addition, the literature suggests that all patients experience some degree of SIRS during cardiopulmonary bypass. So no matter how healthy you are, or if you had no history of serious infection, cardiopulmonary bypass will lead to some degree of systemic inflammatory response. So that's a huge problem that us as perfusionists face during cardiopulmonary bypass. And then so if we get into the general mechanism of action, recent research suggests that activation of the vascular endothelium through cytokine-mediated events initiate SIRS. As we all know, this can be caused by neutrophil-related damage. So cytokines released by the vascular endothelium will call neutrophils over and basically cause a lot of damage whenever it's activated. So our aim during cardiopulmonary bypass would be to kind of attenuate this response so we don't get any neutrophil-related damages that can be detrimental to our kidneys and other organ dysfunction and cause other organ dysfunctions. The most common cause of these events are attributed to blood contact with foreign surfaces. As we know, we run, during cardiopulmonary bypass, we run the blood throughout the entire system, and our oxygenator has a huge surface area. So there's a lot of contact that the blood makes throughout our circuit, and it can cause a huge inflammatory response. And then foreign surface initiates simultaneous activation of extrinsic and intrinsic clotting cascade. Specifically, our circuit causes the intrinsic clotting cascade, and then the kinin system, which will eventually lead to vasodilation and can cause edema during cardiopulmonary bypass. The complement cascade, which is initiated by antibodies, and actually that will eventually lead to the neutrophil damage as it activates neutrophils. And then the fibrinolytic system. So that can be a huge issue postoperatively when we're worried about bleeding. And if you look on the right, you can kind of see a little bit of a summary regarding all the things that can be caused by blood surface interaction with our cardiopulmonary bypass. And definitely a lot of cytokine production, which can cause a lot of damage to our patient. Okay, and then here's two pictures basically of what I kind of wanted to look at regarding to platelets. So if you look on the left, you can see a picture of non-activated platelets. And then on the right, you can see activated platelets. Their structure is pretty different. You can see how the activated platelets have pseudopods. So that makes it a little bit easier for them to adhere to our tubing. And then the non-activated platelets are generally a little bit smaller, and they're circulating throughout the circuit, so you don't really see too much potential for adherence to the wall. And then, so when activated platelets, they change shape, develop pseudopods, express surface receptors, they aggregate, which can be a huge issue for us because they can cause strokes or embolisms. And then they release contents from their granules. And then also this activation could lead to a huge platelet decrease, which can eventually cause a need for transfusions after postoperatively. So it can also cause thrombocytopenia, and then it may require postoperative transfusions, which is bad. As we all know, we want to avoid transfusions as much as we can. It can cause trolley, which is bad for the lungs, allergic reactions, etc. Okay, and here's our platelet activation biomarkers. So for our specific experiment, it's a pilot study, so we're kind of just looking at right now, we're gonna be looking at hematocrit and platelet function, or platelet quantity, and then we're gonna be looking at the function a little bit when we start getting into TEG. But as you can see, there's tons of research out there on different ways we can assess platelet function. There's substances released from granules, specifically alpha and dense granules. Alpha granules are going to release more protein related biomarkers, and dense granules are going to release more chemical related ones, such as thromboxane A2 and serotonin. Those are vasoconstrictors, which would be bad for the patient. And then there's other common biomarkers such as P-selectin, there's histamine, and there's tons of other receptors that we're kind of researching a little bit more so we can see how we can assess this platelet activation during cardiopulmonary bypass. Okay, and then for the prevention of cardiopulmonary bypass, or for platelet activation, the goal is to prevent the response or the formation of platelet aggregates during cardiopulmonary bypass. There's many ways that we can kind of prevent this activation. We can either modify our circuits, we can incorporate mini circuits due to the decreased surface area, or we can also add ultrafiltration during cardiopulmonary bypass. But the one that we're going to be discussing today is going to be biocompatible circuits. And there's also another option that we have. We can use drugs to try to attenuate this platelet activation. Okay, so biocompatible circuits. So they're designed to mimic the endothelium by repelling platelets and reducing the degree of inflammatory response. Common types of coatings include polyethylene oxide, polymethoxyl ethyl acetate, otherwise known as PMEA. There's heparin coated circuit, as well as sulfate and sulfonate groups. Our specific experiment, we're going to be looking at two different circuit coatings. Trillium by Medtronic, which contains covalently bonded heparin and sulfate/sulfonate groups. So there's different types of circuits out there in the market that use different methods for repelling these platelets or just not allowing them to adhere to the tubing wall. So the sulfate and sulfonate groups basically cause a negatively charged tube, much like our endothelium, which is going to repel the platelets and not let them adhere to the wall. And then heparin, that's another good way to prevent that adherence. And then for X-coated by Terumo, we're going to be using PMEA. That's also great. It's a polymer, so it basically causes an amphipathic wall, so the plates are not able to adhere as easy. Okay, so for our specific experiment, we used 15 liters of bovine blood. I basically would just pick it up at the slaughterhouse, and then I would insert 20,000 international units of heparin along the bucket, so I would try to attenuate the platelet activation as much as I can when we were harvesting it. And then we would use a CBC. We would run a CBC for it, so it would give us a ton of parameters such as platelets and hematocrit. And then I would dilute the blood as much as I could to achieve a hematocrit of 25%. This bovine blood would have a super high hematocrit, so there was definitely a lot of hemodilution that was going on. And if you look at that picture on the left, that's basically the concept circuit that we used. Basically, I would attach a filter to the bucket. I would attach a filter to the line that was inside the bucket, and then basically use counterclockwise direction to push it into a cylinder. And then once I had a certain amount that I wanted into the cylinder, I would take off that filter, grab that tubing, and then insert it into my reservoir. And then that would basically give me a way of measuring how much blood I wanted to add into the circuit. And then once I got the amount that I wanted inside the circuit, we would do the math to calculate how much crystalloid we would need to insert to achieve a hematocrit of 25. And then we would basically chase out the blood, and then that would give us our hematocrit. So that way we maintain some sort of consistency regarding all the samples. Okay, and then basically all of our experiments would be run. We would basically run the blood throughout our circuit regarding each circuit coding for 55 minutes, and then we would assess at 3 intervals. So we would do at 5 minutes, we would start warming to 37 degrees, and then once we got to 5 minutes, we would start cooling to 32 degrees, and then once we got to 30 minutes, we would start raising the temperature back up to 37 degrees Celsius, and then samples were collected for plasma after each interval and a complete blood count. And then at the 55 minutes, we would get a collection sample for TEG. So that would kind of give us information regarding platelet function and fibrin interaction at the end of our runs. And then we had 16 total runs, 11 with Trillium and 5 with X-coded. And that was just those numbers. There's no specific reason why we use that specific run number. It's basically the funding that we had, and we wanted to get as many runs as possible. So those are the type of circuits that we had at our disposal. Okay, and here's another view of our setup. That's a heater cooler you can see on the right, Soren 3T. As you can see, that's when we're cooling to 32 degrees, and then we would attach that to the left, that system on the left. As you can see, we had to salvage a ton of pieces. That centrifugal pump on the right, we had to grab it basically from another machine, and then we had to kind of like tape down a ton of tubing and stuff like that to like not make sure it doesn't move anywhere. And then we would just run it. We would run it for 55 minutes, and then we would collect samples at each interval. So that we would use that as biomarkers to assess platelet activation at each interval. And then we wanted to see if there was any trends throughout cardiopulmonary bypass. Okay, and then for our results, so as you can see on the box and whiskers plot on the right, at first glance, you can see that it appears as though X-coded shows a larger difference after 55 minutes. And then Trillium on the left shows a little bit more of a subtle difference once you get to 55 minutes. But if you look at the table on the right, it might also show, it also shows that a little bit. You would think, oh, well, there was a huge difference. This is in thousands. You would think, oh, this shows a huge difference with X-coded. So that means X-coded is a terrible circuit. But also we also have to take into account that there was a smaller sample size for X-coded, and our p-value would be more significant for Trillium. However, sample size does play a role, because the more samples you have, obviously, the more sensitivity you're going to have for your experiments. You're going to be able to measure those smaller changes. And one thing I personally found interesting is that if you look at Trillium from 30 to 55 minutes, you would see actually that the platelet number increased a little bit, which I thought was super interesting. That once we started rewarming, we saw an actual increase in platelets after it had already gone down a little bit. Who knows, maybe the aggregates disassembled and just came back into the circulation. But we do know that warming kind of did decrease the difference in platelets. Okay, and then that was within each coding. But if we look at between each coding, you would see the differences regarding time and the p-value as well. You would see also those same changes. For Trillium, for Trillium, the platelet number increased. For some reason, we want to look into that a little bit more in our next study. And then at 30 to 55 minutes for X-coded, it still decreased, but not as much as 5 to 30 minutes. And so if we look at the time interval platelet change, so from 5 to 30 minutes, you can see a drastic change in both circuit codings in regarding to platelet number. You can see that there was a significant reduction in platelet quantity from 5 to 30 minutes, and a much more subtle one from 30 to 55 minutes. And we thought that was really interesting, that you would see a huge decrease in platelet number at the beginning of surgery instead of at the end. So we're going to investigate that more in our future research. Okay, and then we also took a look at hematocrit just to kind of see if our circuit was just destroying everything, all of our blood components in general, or was it just looking at destroying platelets? And then we also know that hematocrit does play a role in platelet activation, as it causes marginalization to the tubing wall. And as you can see, the hematocrit difference within each coding and the mean standard deviation. So from 5 to 30 minutes, you saw a percentage difference of 1.52%. That means our hematocrit decreased from 5 minutes to 30 minutes. And then on X-coded, it also did by 1.10. As you can see, there was a bigger change in trillium, but again, that might be due to the sample size that we saw. However, we did see for X-coded, there was a much larger p-value, which would also indicate just sample size errors. Okay, and then the hematocrit difference between each coding and mean standard deviation, we kind of see those same changes. Hematocrit also did decrease throughout surgery, but I think to a much lesser degree than platelets did. Okay, and then here's where it kind of gets a little bit interesting. So we actually used a tag. We used platelet mapping using a tag 6S. And basically after speaking to the hemanetics consultant, she recommends that that we use the tag 5000, but we use the tag 6S because we also heard that ECMO centers use that all around. So we definitely wanted to look at, so she told us for specifically for platelet mapping to look at the HKH value instead of the ACT-F and the ACT-ADP, just because we're not sure if that correlates with what we were looking for a little bit more, and it's not typically used during cardiopulmonary bypass. So she suggested just like an HKH, and we did see some interesting trends as well. So if you look at baseline X-coded, the maximum amplitude, which on TAG, that means that it's the strength of clot formation. So it'll get us kind of some indicators of platelet function and platelet fibrin interaction and the clot strength in general. For X-coded, our initial samples was over 71, and that's millimeters. And then for baseline trillium, it was at 70 millimeters. So as you can tell, pretty strong clots. And then after 55 minutes through running it through the circuit, we wanted to assess that clot strength again. So we looked at HKH for X-coded, and it went down to 69.7 from over 71. And then for trillium, it went down to 67.28. So we're starting to see that cardiopulmonary bypass may actually decrease platelet function and interaction with fibrin after you're running it through the circuit, which is kind of what we expected. And then so we did run it on, so we can trust these p-values a little bit more because we did have the same sample size for both of them. And it shows a significant p-value for both of them. So that was something that we were definitely excited about, that we get to see that cardiopulmonary bypass does decrease platelet function as well. And then so basically, if we're looking at all the entire data and bringing it together, trillium did show statistically significant difference in platelet count. Larger sample size may have played a role. So that's what I was talking about a little bit with the p-values. It might have manipulated them just a little bit. However, in both circuit codings, there was a total decrease in both platelet quantity and hematocrit. And we saw that huge difference more in the 5 to 30 minutes than in the 30 to 55 minutes. And we're still kind of investigating why that is, but we do know that we saw a huge decrease in blood components at the beginning. It might be due to the cooling section of it, or maybe I was moving around the samples a little bit too much, but we did see a huge trend on that. And then TEG showed a statistically significant decrease in HKH in both circuits. So we do know that platelet function did decrease at the end of our experiments. And then so overall, when we looked at all the data and kind of bring it to more relevant to us, so we were unable to confirm optimal biocompatible circuit. That's just because we were unable to compare that to a control group, because we were honestly not able to find any sort of uncoded circuits. It seems that most of the companies are kind of just focusing on coded circuits, and it's hard to get a hold of it. So we weren't able to compare it to a control. So we were kind of just looking at them and them together. And the literature does show that circuit codings do play a huge role. So that's not the question that we were trying to answer with that. And then we did see that platelet decrease is a result from cardiopulmonary bypass, as suggested by our extrinsic biomarkers, such as platelet quantity and platelet function that we found through TEG. Intrinsic biomarkers may give more information regarding activation. So at the end of our samples, at the end of the sample collection, plasma sample collections that we would do after every interval, we actually collected those samples. They're in the freezer right now, and we want to measure biomarkers such as platelet factor 4 and beta thromboglobulin. So we're going to be adding that in our next study. This is a pilot study, so we're going to expand it a little bit more after that. after we do more samples and stuff like that. But we do still have those plasma samples, and we're going to see the intrinsic activity of the platelets later on. And then so potential factors of platelet reduction could be the temperature. So I did cool the temp. That's why we kind of cooled the temperature a little bit and then brought it back up. So maybe that played a role. We did see that there was a huge decrease in platelet number when we were decreasing the temperature. Maybe the time of bypass has some sort of influence. At the very beginning, we did see a huge decrease in everything. So maybe the acute response to the tubing and stuff like that caused that huge difference. And then maybe the blood components just kind of got used to the circuit and stopped activating after that. And then our shear stresses. So we do know that hematocrits cause higher RBCs in the blood. So the more RBCs that we have, the more they kind of cause shear stresses with the platelets and push it towards to the wall and cause more platelet activation. And then drawing samples as well. So I tried as hard as I can when I was doing the samples to not push air into the circuit, because I know that would cause hemolysis. But perhaps when I was drawing those early samples and moving stuff around, maybe that had a huge impact in the platelet reduction seen at the beginning. And clearly hematocrit we were looking at too. The higher the hematocrit we saw as well, the bigger difference in platelet reduction that we saw. And then for future suggestions, so we used the TAG 6S, which uses resonance frequency. So that's not typically advised for the purposes of bypass. However, speaking to the hemanetics consultant, she said that the HKH value was something that we could look at, but she suggests for our next experiments to use a TAG 5000, which uses a torsion with a pin. So basically, you're going to spin a whole blood sample, and then you're going to see the fibrin formation off that. So that'll give us a little bit more information regarding our R value and stuff like that. And maybe we can start bringing in other coagulation factors into the mix and not just look at platelets. And then I would also suggest one of our biggest things would be to include larger sample sizes. That's just due to the impact that it had on p-value. As we know that the higher the sample size, the more significant p-value we'll get. So we kind of hope to run more larger sample sizes, so we can also increase the sensitivity of our test, and we can see those smaller changes between each experiment. Okay, and here are my references. Okay, and then that being said, I'll open up the panel to any questions if there's any.
Very good presentation. It was very nice. Thank you very much. That was very scientific, very good. Got one question. You basically were showing that you saw your platelet counts increase when you went to the rewarming phase. And that's true, because the platelets aggregate when you're at cooler phases. They basically clump together. And therefore, you're going to see that. You're going to see that with any circuit at that point in time, where as you rewarm, and even with, and again, I agree with you, the TAG 6 is not a way to go to measure that. You definitely need to go with a TAG 5000. Mm-hmm. So, I think you're going to show a different result in the future when you use the TAG 5000 for your study and the following study of this group. So my advice would be, but you're definitely going to see platelets, increase in platelet count. When I did the studies with platelets and TAG, we always saw that as you rewarm. But excellent presentation.
Oh, thank you. Yeah, we found that super interesting as well. We're going to investigate that a little bit further in our future experiments.
I think that's pretty much all we have time for, right, Susan?
I think so, yes. Thank you so very much. These are great.
All three of y'all did really well.
Very good. Yeah.